Okay, so welcome everyone. Thank you for attending today's webinar. So we have some exciting news. We are adding one more IP to our IP catalog as we're building it out here. So this is going to be our first neuromorphic accelerator IP. And this is based on the ReRAM technology. We've partnered with BM Labs that created this IP. Smart, if you can go to the next slide. Yeah. So Samarth here, the CEO of BM Labs, is going to be introducing BM Labs and the new IP, and then they're going to show a demo of how to verify this IP inside the user project, and then they're going to show the roadmap for the upcoming new IPs based on neuromorphic accelerators. And as always, we're gonna be sending the webinar recording to everyone. And if you have any questions, please use the Q&A feature in Zoom. So yeah, take it ahead, Smarth.
Hi everyone, I am Samar Jain, the CEO of BM Labs. Thanks Marwan and Jeff for the introduction. So today is about turning brain-inspired compute into shipping silicon, right? So our company makes ASIC IPs for neuromorphic applications, and we are happy to announce that our neuromorphic IP is now available on Chip Foundry platform. This means you can seamlessly integrate our compute in memory IP into your SoC projects and tape out using upcoming shuttles. So we build neuromorphic semiconductor IPs, which are energy efficient. As Marwan mentioned, it's based on ReRAM. Basically, it's a ReRAM crossbar accelerator with mixed signal peripherals, right? So it's not just single ReRAMs, it's a full working macro. So our mission over here is to bring brain-inspired computing to edge devices via our crossbar series chips. What makes us different is that our chips can do compute in memory, plus it's extremely easy to integrate using open source flow tools like Cocotb or OpenLane, right? Which I think most of the people might be aware of over right here. So if we compare brain and GPU, brain is essentially event-driven, ultra-low power machine, or you may say that. So our accelerators are inspired from that architecture. But nonetheless, GPUs are very good at dense throughput, and we see that GPT nowadays is very popular, right? So it's very good for dense throughput, but it's less ideal for continuous, always on task. And that's where our IP comes in. Our IP behaves like brain, but on silicon. So over here, you can see that the neuromorphic crossbar 32 cross 32 macro and how it can be integrated into Caravel SoC. So it's a macro which consists of a crossbar array with its peripherals like decoders, ADC, memory controller, because in the end, it's a memory with compute. And it also has an inbuilt wishbone bus slave, which seamlessly helps you integrate with RISC-V, in this case with Caravel, right? So why does it matter? Because it reduces latency, which previously you would have to fetch from EEPROM, memory, like data from external outside the chip. So it reduces latency plus power because everything now is happening at the memory array. So we are happy to announce that our macros will be available for prototyping in the upcoming Chip Foundry shuttles. So if this is your first silicon, I would suggest book a slot in this. So So how do you get started, right? So we provide a very easy integration roadmap over here, which is you can integrate our macro and verify it using open source tools like Caravel, Cocotb. So you can perform RTL verifications, and then you can use OpenLane, and directly you can send it to tape out using Chip Foundry. So the repo link is provided over here, and I will be showing you how this can be actually done within minutes. So the macro is essentially having an interface, a digital interface with using a wishbone, and it is a 32 cross 32 crossbar array, which you can access individually. So in this demo, we will be writing the data into the neurons, the weights, and then we'll be reading out the data, verifying the functionality of the IP. So let me bring the video over here, demo video. Yeah. So generally for Chip Foundry platform, what we do is that we can fetch a user project example, which contains the basic setup, right? Which I think is readily available on Chip Foundry website. So what I will be showing is how you can fetch our IP and integrate it into this Caravel example, right? So over here, you can see our GitHub example for the Caravel user, Neuromorphic crossbar 32 cross 32. And then we try to install the IPM. If you don't have, you can just install it using this command, right? So let me just show you. This is the repo with all the Caravel user template. And just we can copy this installation command to fetch our IP from the IP manager. Oops. Let me change. Yeah, so if we just quickly move forward with this. Yeah, so I'll try to install, but for my case, it's already installed, so it shows no need to install again. And then we can just copy how to install our IP models. So you can just copy this command and it will automatically install our IP models, which you can use for verification. Okay, there's some error. Yeah, so if you, because we already had it installed, so we have to reinstall it. Okay. Yeah. So this will help you install our IP models from the IPM. So now if you see in the Caravel user example, right? So generally this IP folder is empty when you clone generic Caravel user project. So after you run the IPM command, you will see this Neuromorphic X1 32 cross 32 folder, which contains the documentation, which is the power consumption, timing diagrams, all of this. It contains the top level macro GDS. It has all the HTL files for your simulation, verification, like behavior models, wrappers, stuff files, whatever you need to run. It also has, one second. Yeah, it also has the left files and the liberty file, which you will read in your OpenLane flow, right? So this is what you just need to get started. So now I would like to show you a simple write operation into the memory, the neurons, and how can you read it, right? So you just, after once you have done this, right? So you have to just do, you have to just run the Cocotb by typing make Cocotb and verify space the name of the test bench, which is present in the HDL folder, in the Cocotb folder, if you see the repo. So once you run this, what we're trying to do in the firmware, which I will be showing the firmware later once it's completed, we are trying to write a data into the neuron, right? So right now it's saying starting ReRAM word test. So it's trying to write. So once it finished writing, so yeah, these are some internal signals. So if you would have seen, let me just go back a bit. Okay. Oh, sorry. So it says the test has passed, right? So what essentially happened is we were trying to write this data which combines the address, that is XY coordinates of the cell, and the EF is the data we are trying to write to the neuron, right? So this is the internal signal of the IP, the FIFO, which we have. So this is what is printing, but you can see it started ReRAM test, followed by starting the write and read test, and then it is processing the read, which we'll be seeing with the waveform later, but it's just printing over here, just to know that the code is working. And then once the things are done, we see it's passing. So let's see what exactly happened inside. So if you want to see the output files, you can go to the Caravel user and you need to go under the Cocotb. So Verilog DV, and under Cocotb, you can see the RAM world. So let's open the firmware, which so the firmware is essentially the code. So once you get your chip back, right, after you do the tape out, so you have to write a firmware in the management SoC, which is a RISC-V. So this is the RISC-V code. You would have to dump it. So let's see how you can do the similar test once you get the chip back. So over here, the initial files, the initial lines are like just initialization of the GPIO pins. But the main thing over here is the single write and single read demo. So over here, you can see the address and the data we are trying to write to the synapse, right? I mean, to the neuron. So it consists of the address followed by the last EF is the data. So I'll write and comment later on this. Like, how do you know which is the coordinate of the cell and what is the data? So we send the W data using the wishbone line, and then we read the data from the address once it is done. And then we just toggle the GPIO pin in the end just to know that the test has successfully ended. So maybe once you get the chip back, you can just put a logic analyzer on the GPIO pin and you will know that it has toggled from 0 to 1. That means the write operation has finished. And yeah, I think the last function was simple read wishbone function. So which we are using over here. We just input the address and we read. So let's see the waveforms, actually what is happening. Oh yeah, this is the Python script you were seeing. So it reads the GPIO status, right? So I mentioned we are playing with the GPIO pins, right? When we are doing the read write operation to know physically, is it actually happening inside the chip or not? So this Python code you can use to read the status of the GPIO pin and print the status and the checkpoints. So over here you can see we did a write. So as soon as it was 1, GPIO was 1, we did the start write read, and then we waited for the process, and then when the GPIO went 0, we completed the read and write operation. Yeah. So I think over here you can see the printed statement which we were seeing in the terminal previously, right? So next we can see the waveforms, because in Cocotb we can explore the waveforms of internal signals. So we will try because the IP has a wishbone interface, so we'll try to see the wishbone signals. So you can use GTK wave to open the waveform file. And we will try to find the wishbone signals. So the IP comes with standard wishbone protocol. So you can see all these are the wishbone signals. We'll try to add them in the display. Right. So in standard wishbone protocol, when we are writing the data, right? So that time the write enable signal will go high, and then when we are reading, it will go 0, correct? So we'll try to go first to the write segment. So we know that initially the CPU will be starting, so there'll be a lot of addresses because it's a common wishbone for the full management RISC-V. But we will zoom into the point where we actually send the data. So if you remember, we were sending data to this address, which is a 32-bit address. And the data was 8, 9, A, B, C, D, E, F. The EF was the data, and rest all is the XY address, the row address and the column address of the cell in the crossbar. So because we are writing, so the write enable should be high over here, and the data is present. And then we get an acknowledgement signal, which means that our IP, which you're trying to verify, has successfully received the data. So it gives an acknowledgement, right? So after that, the IP will have a data and it will write using the FIFO internally, and will take a couple of cycles. So we can see that now the wishbone is handed over to the RISC-V for other tasks while the IP is writing the data. So to see where we did this, so you can see over here, we were trying to write the data to this address, and the data was 8, 9, A, B, C, D, E, F, where I can explain over here what is a row address structure. So the bit, I think 30 to 26 would be, I think, rows. Oh, I think 29. Let's check it. Yeah. So this is the register format in the IP you need to send. So if you want to specify the row address, it'll be on the 29 to 25 bit in the crossbar. So crossbar is just like a chessboard, right? So it has XY coordinates. So the row versus column. And the column address similarly will be between 24 to 20. And then the EF was the data we want to program into neuron, which is essentially a ReRAM, which is mimicking a neuron over here. Right, so 720 bit is the data bit, which is EF in our case. And that's what we saw, that we sent EF. Now, yeah, so we can see the acknowledgement has been received and the transaction is ended. So now the IP is taking time. So let's go to the next cycle when we are trying to read, which is the wishbone will have WE underscore I as 0 because we are trying to read. So we are trying to read the same address, and we see that the read line, which you can see over here, the output from the wishbone is giving EF. So it took some time to write into the neuron, and then when we give a read cycle, we can read the same data back from the neuron. So it's essentially like a memory over here, right? And we can see the other signals like CYC, which are typical wishbone signals. Yeah. So that is how you can easily integrate our IP using Chip Foundry IPM and do a verification. So moving forward, I would like to explain how we're, hello?
Martha, it's Jeff. Yeah, I'm just thinking, I'm wondering if it's worth talking about a little bit. I don't know if you already plan to do that, but talk a little bit about kind of what you've already done in terms of taping out and testing, especially like the because of the whole technology is based on your ReRAM cell that you had been developed and tested, right? But we had a couple
Yes.
of questions around that, so it might be valuable just to comment on that a little bit.
Sure. So we have done about 2 SoCs on ReRAMs, and we have couple of data if the customer requires for those chips, right? And yeah, so we do the testing, reliability testing in our labs for the Skywater ReRAMs. And yeah, we do provide the data if the customer requires regarding the ReRAM cells, the modeling of the ReRAM cells, and so on.
And there was a question around, did you develop that, what the kind of the cell itself is something that you developed, correct? The ReRAM cell, bit cell?
Yeah, so we just take the film from the Skywater or foundries, and then the cell is developed by us, the array is developed by us, and the decoders. So what essentially I showed on this slide, so the whole crossbar cell array is developed by us, decoders, the memory controller, it all comes in the macro with the sensing circuit inbuilt. So the user just has a digital interface, easy to use with existing Caravel management SoC.
Super. Great, thanks.
So going forward, I would like to explain the evolution of the crossbar IPs which we are developing over here, right? So we are moving from crossbar 1, which is X1, which will be totally embedded NVM, which you just explained you the verification flow, right? And then we will be moving to crossbar 2, which is called as X2, which combines NVM plus compute, and followed by crossbar 3, which is a cluster-based crossbar. So the strategy over here is that we want to scale the functionality while retaining in-memory efficiency DNA. So comparing the crossbar 1 and the crossbar 2, the crossbar 1 is a 32 cross 32 crossbar which acts like NVM, embedded NVM, which functions similar to EPROMs, right? But it's ultra efficient because it's inside the chip. You can use it for backend processing if you have a sensor inside SoC. And it's great for IoT application, Industry 4.0 sensors with low latency NVM processing. The Crossbar 2, which is a Neuromorphic X2, is specially built for compute IP with dual functions. So it's essentially an in-memory compute IP. It's great for on-chip data compression and logging. So for example, you want to make SoC for energy meters or medical application, and you want to log data reliably, you can use the Neuromorphic X2 because you can compress as you store the data because it has built-in analog in-memory computing for energy efficient compression. So the outcome from this is low power, smaller latency budget for edge pipelines. Going to our Neuromorphic Crossbar 3, which is a 2D mesh macro. So if you plan to use this IP, you can copy it multiple times. But the Crossbar Macro 3 gives you an efficient way of utilizing these processing element, which is one macro, right? So if you want to do something more intense in terms of application, not just IoT, right? You want to go to edge ML kind of applications. So you would need more weight storing capability inside the chip. So that's where this comes in, right? So it is very flexible. You can copy the macro how many numbers of times you want, right? You can make a cluster of processing elements. You can write weights into different processing elements. And it can give you extremely good throughput. So the application for these things can be edge AI for the first go. You can use on device for speech, facial, and object recognition, right? For like neuromorphic processing. You can make neuromorphic sensors with a camera at the front end, but a neuromorphic IP which is processing it in real time, right? And it's also great for robotics and defense application if you choose to use Neuromorphic X3 IP. So looking at how do we put this in the spectrum of current chips, right? Because there are a lot of other existing chips available. So for example, if you are a startup or if you are a university student and you want to know that if I plan to use X1 multiple times and try to go towards Neuromorphic X3, then where I can place in terms of throughput and latency. So we have used open source benchmarking tool, which is available on our website. So you can go to our website, you can read the references, and we try to compare it with Jetson Nano, which is essentially for NVIDIA chip, essentially for IoT applications, low power, low throughput applications, up to NVIDIA Orion and even Memory X, which are very highly scaled, high advanced nodes technologies, right? So you can see that it comes in a sweet spot with very good low latency and a pretty good throughput, right? So if you would like to replicate this benchmarking, you can check out our website over here, and we could also provide you data regarding that. So we also compared, so I mentioned about throughput, just to put throughput in perspective compared to other existing chip, our throughput is quite superior compared to Jetson Orion from NVIDIA. If you use our IP and make a SoC, right? And it's definitely better than Nano because Nano is for only IoT application. And in terms of die area, because you would need to put multiple of these macros to achieve this kind of performances. So it's comparable. The die area is not that bad. It is only 2 times of the Orion Nano chip, right? But you have the flexibility to change as per your design needs. So to summarize, we are now providing you the 32x32 analog in-memory compute macro, and we also provide documentation integration help. The use cases for our first X1 is industry data logging, medical devices. It's priced at $5,000 for one-time prototype licensing, and it's readily available on the next shuttle from Chip Foundry. Yeah, so I think that's all I had, Jeff. Maybe we can look for questions.
Excellent.
Yep. We have a few questions that we can answer live here. So we have a question: to make sure that the documentation states it's 1 KB, is it in bytes or bits? So the 1 KB, is it bits or bytes?
Yeah, so it's a 32x32 cell, and currently each cell can only be a binary, so it's 1 KB small b. So 1024 cells with only 1 bit of switching in the X1 IP.
Okay. How many level can be used for each bit?
Yeah, so that's a very good question. The prototype IP currently is for 1 bit, but the user can play around with it and achieve higher bits if they need. But 1 bit is guaranteed in the IP.
Okay.
Yeah, so it's like a synapse, right? So they can play with the time of duration they're programming each cell. We give flexibility to program X, the row column with the data they want to program, right? So they can try multiple bits if they need.
Okay. Okay, so there's another question. So during write operations, the address can be selected as part of the data. So bits 29 to 25 to 29 for row, 24 to 20 for column. But how do you know which part of the array is being read?
So when you do the write operation, as you correctly mentioned, that is the row address, column address, and the analog weight you want to program, that is the data, which was EF in our example, right? So once you program it, you send it to our macro FIFO, it programs it, and then there's one more FIFO which you can send the address and read it back. So it's a FIFO. I mean, it's a first in, first out, right? So you can know which address is coming out when you read it.
Okay. Um, so I guess that's a question more for Jeff. How many extra masks does the ReRAM require?
2. It's 2
Two.
layers. Yep.
Okay. Okay, there's another question. Based on the behavioral model, data are popped out when read is issued. Does this reflect on the same IP? When data are read from the IP, can it be read again?
So it's a standard wishbone protocol. You have to do a write operation and then you can do a read operation. So I would recommend to just pull our IP and experiment with it. It's a standard wishbone protocol, even available with chip foundries, other macros. Yeah.
But I think the question, if I understand correctly, the question is if they pop the data out of the memory, does that mean it's gone or can they read it again?
So you mean like if the FIFO you read it, it comes to your management and you have to store it. So yeah, it'll be erased from the FIFO, right? Not the memory. So it's a non-volatile. I think because the user might be getting confused, it's not a SRAM macro, it's a non-volatile memory. So when you are reading, the data is remained in the array until unless you rewrite it with a fresh memory. It's just you are filling the FIFO when you're trying to read for the particular address, but the data still remains in the crossbar, but not in the FIFO. It is erased from the FIFO.
Okay. So yeah. Okay. Good. Seems that the X1 is simply ReRAM. Why do you call it in-memory analog macro?
Yeah, so X1 is actually like you might say substitute for EPROMs, right? But it's right now in you're using for prototype, so we give you flexibility if you want to use it for bitwise manipulations, you can do it, but you cannot do like in-memory accumulation and things like that, which is only available in X2. So you can still do some compute by tricks. There are a lot of tricks in research and publications. People use single cell for bitwise AND operations and things like that, right? But the analog summation of the current is not available in X1, which is only there in X2.
Okay, good. And do you have any data on endurance?
Sure. So interested customers can just request the data. We have data tested across 20 discrete tape-out chips from Skywater, and each chip had couple of ReRAM. So we have test data at room temperature at 125 degrees C for retention. So feel free to contact us to request these data.
Okay, good, thanks. And if at boot, if there's a read request that happens, is the data gonna be random values or is it initialized by something a boot?
So it depends. There can be two scenarios. ReRAM generally needs first cycle of forming, which is like when you buy it fresh from the foundry, it will be in a high resistance. So ReRAM is just a tunable resistor or like a neuron. So when it is fresh out of the foundry, you will read everything zero from the memory if you try to read. But once the initial forming is done, right? So you need to form only once, and then the data can be random depending on what the data was stored previously. So we give you the flexibility to play with the memory and just provide you a digital interface. You can write your firmware to take care of those things.
Okay, good. And can you read oh, sorry. Can the read circuits and ADC handle multiple bits?
Theoretically, yes. I mean, if the user want to play, they can try, but they are designed for only binary operations.
Okay.
Just to say that the sensing margin might not be that great for this, but they can still have some flexibility to play with it. Yeah.
Okay. Another interesting question. So, what would be the simplest neuromorphic application to start on the IP?
Oh yeah, it's a very good question. So for the Neuromorphic X1, I would recommend use these IPs for applications like logging, right? So for example, you want to log energy meter readings, use it over there because it can give you large endurance. It can work at high temperature. As I mentioned, we have 125 degrees C temperature readings. So you can use it for embedded memory for logging purposes, or you can use in IoT applications where you just want to not continuously read, but just store the memory and leave it as it is, right? So that's where it will shine.
Okay. Good. So, there's some confusion about how it can handle multiple bits at the interface if it's binary. So the question is, do you allow direct visibility to the ReRAM array without going through the wishbone bus?
No. So as you saw in our slide, the only interface for the user is the wishbone bus, which is connected to the management SoC. And once you send the row address, the column address, and the level you want to program it, right? So right now for X1, we recommend users to use only two levels. That is FF or 00 kind of thing. It will give you the best results. But if you would like to play with something intermediate, you can program it, but it will be difficult for you to read because we recommend use only 2 bits. So you have the flexibility to choose the cell in the crossbar with row address, column address, followed by the state you want to program it in.
Okay.
And then to understand that, because I was curious, so when you go back and read, you get back the level in that you get back the level of the programming, and when you go back and read it, you get the level that you programmed it originally.
For Neuromorphic X1, it will just threshold it to high and low value.
Okay, so
We haven't
give you a binary value back. So I think that was the question: is how you can potentially read back different levels if the interface today is only providing you binary read back.
So yeah, that is our roadmap for X2, which we are planning next year quite soon.
Yeah.
We will be enabling with the same IP, but multiple levels. That's how you can do compute with it.
Okay. There's another question here that I actually can answer. So can you please emphasize what is the actual offering? Is it the macro, and if so, what are the X1, X2, and X3? So the offering here is the IP, so it's the macro itself that you can integrate inside your design. And the difference between the X1, X2, and the X3 are just 3 different generations of the same IP. So right now we're in X1, so that's the offering that we have right now. And as Samarth just said, they're working on X2 and X3. So it's going to be incrementally announced to the community. So yeah, so that's basically the offering. Okay, another question for you, Samarth. Was it tested in temperature?
Yeah, so it's we have tested it at endurance of 125 degrees C. So we heat the chips and we check. So we essentially program the ReRAM for 24 hours at accelerated temperature. We have multiple of these SoCs, and then we read back each cell to make sure that the state remains same. So we do offer this data for interested customers, right? So we provide endurance at elevated temperature and at room temperature.
Okay. And regarding your second question, they do provide the data for endurance and retention if you need it. You can contact them directly, and they were gonna provide it to you. Okay, so another question: how can we refill the FIFO after the read with the data sorted inside the crossbar? So, for example, we store EF at 00 or address 0. How can I read it multiple times?
Yeah, so essentially, once you read the data from the FIFO, it is lost from the FIFO. Then again, you have to read the same cell and it will enter the FIFO and then you have to empty the FIFO. So there's only one input FIFO and one output FIFO in this scenario. Does that
Oh,
answer it?
so the question is, how can they refill the FIFO?
They can just keep giving the read command and they can just keep filling the read FIFO. And for the write FIFO, they can just keep looping the write command because, as I mentioned, this IP is like EEPROM. So it has a buffer, which is the FIFO. So you cannot write it in one cycle. So you send multiple instruction. And as I showed in the timing diagram, after some cycles, we got the read, we asserted the read instruction and we read it. So during that time, the CPU was busy and the IP was writing the cells with the FIFO already filled.
Okay. Yeah, makes sense. Okay. Next question is, I understand that there's flexibility for the pulse width and amplitude in programming the bits for ReRAM. Can the read circuits handle multiple bits of output precision?
So as we show over here that the decoder circuit, which is providing the pulses of multiple amplitude, is inbuilt the macro, so the user doesn't have access to that. It's all controlled by the memory controller, right? So it's all taken care by the memory controller IP, and the user doesn't have flexibility to do it. So it's all done within the memory controller.
Okay. Okay, so there's a question about endurance. How many times can you read or write before the ReRAM fails?
I think the endurance data which we will share with you, at least 10K cycles are available for all the cells in the working cells in the crossbar array at elevated temperatures, which
Okay.
is a typical number for a ReRAM, right? So if you read the literature survey, it's a typical number for a ReRAM, about 10K cycles.
So the last question we have here, so each one of the 32 by 32 cells can be used to store 8 bits of data, 0 to 255. So it can be considered as 1 kilobyte data.
So that's a very good question. And as I mentioned right now, each cell, because of the sense circuitry, is only available for, like, you can sense it only either 0 or 1. But we have data that the cells in the crossbar can be programmed to multiple cell, which will be in X2, right? So currently the IP, to answer the question, currently the IP is 1 kilobit, which is small b. It's not 1 kilobyte, right? So that is why we presented a roadmap that the cells are capable of doing it. It's just we will be introducing new peripherals in X2.
Okay. How to change the cells? We want to fill the read FIFO without issuing the wishbone right on that cell. Specify which cell in the crossbar we want to read because the read address is fixed.
So that read address is actually the one where I showed was 3 followed by 60 and C, the 32-bit. That's a slave address. That's not the cell address. The cell address is sent in the wishbone data line. So as I mentioned, the data bus is a 32-bit in which we have segregated, as I showed in the example, some bits for the row address, some bits for the column address, and some bits for the data. So that's the actual data. So please don't get confused with the wishbone address, which we are sending. That's the slave address of the IP. So because I mentioned we have a wishbone slave inside the IP, right? And the address in the crossbar is actually sent through the wishbone data bus itself. So in this way, you can also imagine you can copy paste the same macro multiple times and use different wishbone addresses if you would like to do it.
Okay. Good. That's about it. We don't have any more questions. Actually, we do. If I recall correctly, in the wishbone specs, you can't provide data in when you are performing read. What happen that happens on write. Specs, you can't provide data in.
So it's a FIFO, yeah. So you might have to maybe just explain the FIFO concept again a little bit, Samarth.
Yeah. So actually for the wishbone, how it works is it has a data line followed by some CYC, strobe, acknowledgement. So the acknowledgement is the only signal coming from the slave, right? And the CYC strobe all controlled by master. So when you want to write a data using wishbone, first thing is you have to make sure that you send the correct address of the slave. That's the address of the slave on the address line. In our case, it was 3 followed by 6 zeros and a C, a 32-bit address, right? And then our slave IP is a custom slave, right? So it has a normal interface, but the data which comes in at every acknowledgement, we will be sending maybe 132-bit, then we will be sending acknowledgement, and that will enter into the FIFO. Then again, we will be sending one more data, and the slave will send back the acknowledgement, fill the next FIFO chain, and it'll just keep on going until unless you fill the full FIFO in the slave IP. Once the slave IP has the full FIFO, it will stop sending acknowledgement, even if you try to push the data in, right? So that's how you would know in your firmware that the FIFO is full. Either you have to use your wishbone for different purposes, or you have to wait. So once the write operation is completed, the wishbone will start asserting acknowledgement again. So if you want to read, you will get an acknowledgement back, and then you can read till the FIFO is empty. And then once it is empty, it will stop asserting acknowledgement. You cannot have any read data.
So if I power cycle and I, start up and I start reading, what data? How does the FIFO get filled on a read?
So
Just on a
initially the
read-only
FIFO
operation.
yeah, so initially the FIFO will be empty. And then you would start. So if you want to, if you first read initially, right? So you would send, maybe I want to read a row, comma, column address, and you can send a stream of addresses you want to read. It will start filling the FIFO and then start pushing the data back, because it requires some read cycle, so it will just fill the FIFO.
So you fill the FIFO with addresses you want to read, but you indicate that you don't want to set the data, you just want to read it. Is that what you're telling me?
Yeah, so you can send like multiple addresses to read, and then use the FIFO to read it one by one.
Okay.
So it just because it's like a EEPROM IP, it requires time to program. Like rightly, one of the viewer asked about the Pearls thing, so it takes multiple cycles. So we just use a FIFO to pipeline the things.
Okay, so we're getting more questions here. So is the ADC resolution fixed? If so, are you planning to make it flexible in the future? I understood that the current X1 IP has 1-bit cell, but the analog accumulated current received by the ADC could need to up to 5-bit resolution.
Correct. That's a very good question, and rightly pointed that for Neuromorphic X2 to X3, we will be supporting up to 5 bits, because as mentioned, for multiple bit, you need 5 bit of resolution to do any kind of compute. So for X1, it's just 1 bit, right? For X2 and X3, that's where the change is going to happen. So the user doesn't have the flexibility. It's just if they want higher bit, they would have to opt for the next generation of the macro.
Good. Each one of the 32. Okay. I think we already answered these, right?
So is there, I think part of the confusion too, maybe, Mr. Mark, did you describe the analog, signals related to the IP?
So the IP essentially has, so if you go to our website, or even if the Caravel user project, if you go under the docs, you will find a document stating the analog pins, which are all DC supplies. So the analog pins are all DC supplies, and all the pulse modulation is taken care inside the IP. So there is no analog signal for say, it's all DC voltages, which will be provided directly from analog pads in the management area.
So is it true though that when you're filling, so if in the read scenario, because I think there's still a bit of confusion, when in the read scenario, if I'm just trying to read back a set of addresses, I'm going to fill the FIFO with those addresses. Is there an analog signal that's toggled that indicates that I'm not writing data, I'm just reading? Or how does it know not to write? Because there's going to be a data value in the data bus address, right? You're going to have to either provide a 0 or something for that portion of the address.
Yeah, so once you give a read command, it's like it will fill the FIFO, and you can read from the FIFO with acknowledgement pin. And the write and the read overlap is actually controlled in the memory controller. So it's not controlled by the user over here. So we manage how the FIFO, it doesn't write and read the same cell at a time. So there's a write cycle. So for a generic ReRAM, there are about 3 cycles, which is forming, one is programming, one is read. So we multiplex these cycles inside the memory controller. There is no way you can overlap them.
Okay, is there a bit in the data bus that indicates whether they're doing a read or a write?
Yes.
There is.
So
Okay, that's the thing there.
yeah, you're correct about that. So if you would have seen, our bus is the data of the wishbone is 32-bit, and in the example I only told about the 27 so on. The initial 2 bits are the mode set. So it will determine, if you see our data sheet, it will determine 00 is set 0, 1 is reset, like the write read.
Right.
So these bits are used for indicating what you just were asking about.
Okay, so I think that maybe explains it. So hopefully that clarifies the mode or how you operate. So when you're writing you have a mode set when you're filling the FIFO with the addresses and data. When you're reading, you have a different mode for reading back. You're just filling the addresses, but then you're going to be coming back later and reading off the FIFO to get the data back.
Correct. So the user has the full flexibility when he's writing the wishbone data command. He can specify the first 2 bits, whatever he wants to do with the device, the column row address, followed by what data they want to send.
Yep. Makes sense. So hopefully that explains the question around the second one around the data line not set with the master write signal. So you are writing every time you're writing, the wishbone, you are writing addresses every time when you're filling the FIFO. The question is whether you're writing to the to the crossbar, will be set by the mode. Will be, it'll be determined whether your mode that you included in the data bus is a write or a read operation. What's the other one for? So what was the other, we have another question about from the first question there. For each of one of the 32 by 32 cells can be stored 8 bits. I think we answered that question, right? Rowan?
I think this is a duplicate, yeah.
Oh, so there's a duplicate, yeah. Okay. So the X1 version generation, the read sense is only binary, 1 bit, even though you can store theoretically different 8 levels within each cell. The next generation IP will support multiple levels.
Yeah, we covered everything, and we're actually out of time. So,
all right, great. Well, Samarth, I want to thank you very much for presenting. We're super excited, to have you as a partner and have this IP available for Chip Foundry customers.
Yeah, same here, Jeff. Thank you for the presentation.
Yeah. Rowan, you want to close it up?
do you want to go to the last slide, Samarth? Yep. Thank you, everyone, for attending today's webinar. We're looking forward to always seeing you in all our webinars. And please, if you have any more questions, do email us at info@chipfoundry.io. Please join our Discord or Fossey chat to chat with us. And you're going to find the community also there, a lot of people that can help out in your design. And so again, thank you all for joining our webinar, and see you the next time.
Great. Thank you, everyone.